All right, you guys, we're starting the minerals chapter, and this is probably one of the most important chapters. It's really the building block for all of the geology that we're going to be talking about. Now, if you have not read the chapter yet, I would suggest you stop. Go read the chapter and then start this, or realize that you're going to have to go through this twice, because this is the place where if you're not diligent, you can get lost in this class. This is a place where students typically stumble. So, be forewarned, because it's actually really not that bad. All right, now you will be responsible for the 5-part definition of a mineral, and it's really not that tough, you guys. All minerals are naturally occurring, okay? I've got natural down there. They are not man-made. Okay, they are inorganic or non-organic. Okay, so your toenail is not a mineral. That's organic. They're solids. Okay, solid, liquid, gas, only solids, not liquid, not gas. Okay, now they have a definite chemical composition. Now that sounds tricky. Everybody knows table salt, right? Table salt has a definite chemical composition or chemical formula. It's sodium chloride, or NaCl. Every mineral that exists, we can write out a chemical formula. The good news for you guys is, except for like table salt, NaCl, sodium chloride, quartz, which is SiO2, and a couple other real basic ones, you are not going to be responsible for a bunch of chemical formulas. All right, now this last bullet has a star because it is really, really important. Now, just because you're a solid doesn't mean you're what's called a crystalline solid. You need to have a regular repeating internal structure or a internal architecture, a pattern. I have in my classroom a lot of molecular models of minerals, and if you looked at them, you could see the pattern. There's a definite pattern. And what's really cool, if you guys are in the lab, it's that regular repeating internal structure, or that pattern, that gives that mineral, in a molecule, one molecule of the mineral has this molecular structure, but it actually gives a big hand-sized piece of this mineral all of the properties that it has. Quartz, I think you guys all know quartz, SiO2. It's got a very specific structure, and we'll talk a little bit more about it. But it's that regular repeating internal structure, the way that the elements come together, the way that they bond, that gives a quartz crystal every single property that it has. It's hard, it scratches glass, etc. The way it breaks. So that regular repeating internal structure. All right, you guys, so 5 parts: natural, inorganic, solid, definite chemical formula, regular repeating internal structure. Now, you can be solid and not have a regular repeating internal structure. In that case, you are not a mineral, but you are a mineraloid. Glass is an example of that. There's no pattern. It's chaos in that solid structure. So you have to have that regular repeating internal structure. All right, now this slide just kind of goes, what's naturally occurring, what's not. Cast iron, I love cast iron. If you have a cast iron pan, you know why you love it. That's man-made. There's no such thing as cast iron out in nature. Instead, we would look at iron ore called hematite. Okay, it has to be solid. Ice actually is a mineral, but liquid water and water vapor are not minerals. All right, in organic, rock salt, or table salt that we were talking about, the mineral is actually called halite. Remember the chemical formula, sodium chloride. But that head of lettuce you forgot in your vegetable crisper a couple months ago, okay, that's still organic, and so that is not a mineral. All right, what you should have out is a copy of the periodic chart of the elements. There is a scan copy in the weekly folder, and also there is a copy in your textbook. So just look up in the index and pull that out. Now, the good news is that you guys are going to be using this as a tool. I would never expect you to have this memorized. Okay, and so on your first exam, there will be a copy of the periodic chart of the elements, stapled on the back. Now this is your friend, because as long as you can read a table, that means a lot less memorization. Now, if you guys look at that, hydrogen, helium, etc., these are the elements, and elements are the basic building blocks of minerals. There are over 100 known elements. Now, we are really going to concentrate on those, top 4 or so rows, because those are the ones that matter to us in this class. Now, look on the bottom, okay? Names like berkelium and can't even pronounce them, Einsteinium. Those are things that exist for fractions of a second in a physics lab somewhere, and so I definitely am going to be ignoring those. I don't care about those. Atoms are the smallest particles of matter, and it's the smallest unit of an element. That means that if you have a 1 atom of gold, it has all the same properties as a huge nugget of gold. Okay, and I could take that 1 atom of gold and send it off to a really good lab, and that lab could actually come back and say, hey, you have gold. Now, all gold atoms share particular properties, and kind of the easiest thing is they all have the same number of protons, so we're going to talk about that. They're the building blocks of all materials. We're starting with minerals because minerals are the building blocks of rocks, and in order to understand minerals, we've got to understand elements. All right, so here is my copy of the periodic chart of the elements, and you read it kind of like a book. You go in the first row, hydrogen, helium, then you go down to the second row, lithium, beryllium. Now, you guys, this is a tool. This is your friend. What is element number 15? What is the name of element number 15? Okay, I wouldn't expect you guys to know that, but look, you see the 15, you see the P. You're like, well, I don't know what P means. Read. Phosphorus. Okay, you guys, that, you just have a point. If you know, okay, what's element number 26? All right, if you said iron, you have a point on the next exam. You know how to use this as a tool. And all the different ways that we're going to use this as a tool, I'm going to train you. And so you guys, this is your friend. I want you to remember that. All right, we are going to talk about atomic structure, and I think everybody in junior high school made an atomic model. I know I did, and I know it still happens because my sister-in-law is a junior high school science teacher, and her entire ceiling is covered with student atomic models. All right, if you remember, here's just kind of a quick synopsis, is an atom is made up of a nucleus, and that nucleus is surrounded by some number of electron shells. All right, within the nucleus, and the nucleus is actually really little, and so most of the times we exaggerate the size of the nucleus just so we can look inside, because there's some important things in the nucleus. First thing that's in the nucleus are the protons. Protons have a +1 charge, so typically I will signify them with a plus sign. And they weigh 1 atomic mass unit. If you put 1 proton on a scale, it would weigh 1 atomic mass unit. Now, in reality, it weighs something like 10 to the negative 27 grams. It's just, this is a shortcut. This makes your life easier. This makes my life easier. So 1 proton weighs 1 atomic mass unit. All right, also hanging out in the nucleus are neutrons. Neutrons are neutral, meaning they have no charge. Okay, they also weigh 1 atomic mass unit. Okay, so that's what's hanging out in the nucleus, protons and neutrons. Typically, I show the neutron with an empty set. You guys will see that in one of my little supplementary videos. All right, now, depending on what element you're looking at, you're going to have some number of electron shells, okay? As you move down the periodic chart from the first row to the second row to the third row to the fourth row, you're going to have more and more electron shells, and we'll talk more about it. So electrons I always show with a negative sign because electrons have a -1 charge. They are found out in these electron shells. Now, we say that electrons have no mass. Now, that's not quite true, but it would take 2,000 electrons to equal the mass of 1 proton. So we ignore the mass of electrons because even those strange elements that they have, being created for 1 second in a Berkeley lab, berkelium being a great example of that, they don't even have 200 electrons, so it's not even going to measure anything. Okay, so we ignore the mass, so -1 charge and no mass. All right, now this is the way we kind of show this, and I call it the hula hoop model. Okay, you can see the nucleus, and the nucleus has protons and neutrons in it, and it's exaggerated. It's much, much larger than it would be in reality. It's really tiny in reality. And then right here you can see 3 different electron shells. Okay, and so the electrons are found in the electron shell. Now we're going to talk in a second. The first shell can only hold 2, the second shell can only hold 8, the third shell can only hold 8, and so you guys can see that there's 2 and then 8 and then 8. Now, one thing is that, see those two, you can never add a third one in there. And those two electrons in that very first shell, they stay in that shell. Okay, so we're going to talk a little bit more about that here in a second, but I call this the hula hoop model. Now in reality, remember those in that first shell closest to the nucleus, I said there's two electrons. Those two electrons are everywhere at once in this orbital shell. So I can't draw this, you guys. That's why we always go to the hula hoops. It's much easier to draw the hula hoop model. But in fact, the electron shell is an electron sphere. And those two electrons are in there everywhere at once, but obviously they don't want to be near each other. So they just move around everywhere at once, but do not crash into each other because they're both negatively charged, and opposites attract, and like charges, two negatives would repel each other. All right, in that second energy shell, you can see it's also a sphere. There's the 8, and the 8 would be everywhere at once, and the third one, 8 everywhere at once. Now, that element happens to be argon. If we've got full first shell, full second shell, full third shell, and I'm going to teach you how to figure this out. All right, now something that's super important, you guys. Let's say I had a little quiz on this or something, and I would say, what element did I draw for you? All you'd have to do is look inside the nucleus, count the number of protons. Let's say the number of protons was 3. You look on the periodic chart of the elements, what's number 3? It's lithium. Okay, so that number, when I asked you before to identify, you know, what's element number 6, what's element number, I forgot what I asked you, 26, that's the number of protons, and that's the identifier, that's the atomic number. We are not going to vary this. This is going to always be the same. If we're dealing with carbon, carbon will always have 6 protons in its nucleus. That will not change. Now, sometimes protons and electrons are equal, and if the protons and electrons are equal, that element is neutral. Okay, if there's more protons than electrons, it's got a positive charge, and if there's more electrons than protons, then it's going to have a negative charge. So we're going to have to kind of deal with this here in a second, because in a lot of cases we are going to have charged atoms. All right, another thing that's kind of important, I think a lot of you guys have heard of something called carbon-14. Carbon-14 is radioactive carbon, and luckily you and I are made up of carbon-12, a different form. Now, if you look on your periodic chart of the element, carbon's number 6. Okay, and so atomic mass is the number of protons, and in the case of carbon, it's 6, plus the number of neutrons. So you and I have 6 protons and 6 neutrons in our carbon-12, but radioactive carbon has 6 protons and 8 neutrons, okay, making it different atomic mass. And so when we identify a radioisotope or a radioactive element, uranium-238, okay, there's no element 238, okay, that's its atomic mass, or the number of protons plus neutrons. So that is actually an important number, and we will be talking about that. All right, now I kind of hinted when we were looking at the hula hoop model, and I told you about the 288. Okay, now periodic chart of the element. Pull out your periodic chart of the elements. What happens is that the first electron shell can only hold 2. Okay, so if there's 3 electrons, the third one will go into the next shell. Now the next shell can only hold 8. So if there's an extra one after that 8, then it goes into the third shell. We are only going to concentrate on 288, or the first 3 shells. Now if you look at your periodic chart of the elements, how many elements are in the first row? Okay, check it out. Top row, hydrogen and helium. That's 2. All right, now count the ones in the second row. It goes from lithium all the way to neon. Okay, that's 8. And then look at the third row. Okay, sodium to argon. That's also 8. Okay, and so what's kind of interesting is you see that column that starts with helium, then neon, then argon, then krypton, etc. They are what is called the noble gases, or the inert gases, and their electron shells are completely full. Now, let me tell you a little story about this. Those are the really important gases. Now, I want you guys to go onto YouTube, and I want you to type in Hindenburg. Okay. Now, the Hindenburg was a Nazi Zeppelin. Okay, a Zeppelin is a big blimp. And in order for that to float, you had to put something lighter than air, and air is oxygen and nitrogen, if you remember from previously. Now, hydrogen, being the very first element, the lightest element on our periodic charts of the element, they're like, hey, that's light. Let's pump our Zeppelin full of hydrogen. Okay, so the Nazis, this is before the United States got into the World War II. The Nazis decided, hey, let's scare the United States so that they don't enter the war to fight against us. So let's send our silent, deadly killing machine over to New Jersey and show them, we've got this just monstrously huge Zeppelin, and it's silent, and you're not going to be able to hear it or see it, and it's going to rain bombs on you. Now it exploded terribly, and if you guys watch this video, listen to the announcer. I mean, it's horrible. People died. Okay, what did we learn from that? If you guys go up in the Goodyear blimp, it is not full of hydrogen. It's full of helium, because helium is a noble gas. The electron shell is full. It is non-reactive. There's no way it wants to hook up with anybody else. And so helium is always by itself. But if you guys see a symbol for hydrogen gas, it's always H2. Okay, or think about H2O. It's reactive. It needs to interact with other elements in order to fulfill itself. And so an element or an atom or a molecule is always trying to fill the outermost shell. So in order to become stable, it's kind of funny, guys. Look at that column that starts with helium. That column right there is the only kind of happy, fulfilled column on the periodic chart of the elements. Now, because you're not in class, you don't get all my cheesy examples, but let's call this a soap opera. I remember learning this stuff. It was tough. And I used to call that kind of, in a soap opera, there's always the rich, thin, beautiful people, and everybody else is trying to be like them. And that's kind of what's happening. All of the other elements that are not in that column that starts with helium and then neon and then argon, they are going to all be kind of cross-dressing so that they will have the outside appearance or the electron shell configuration of that noble gas column. Okay, kind of twisted, but it's pretty cool. All right, well, let's check out lithium, element number 3. Okay, lithium has, it's element number 3. It's going to start off with 3 electrons. So 2 in the first shell, 1 in the second shell. If you have 1 electron in your second shell, you're not happy because that second shell is full with 8. And so the question is it easier to ditch 1 electron or to steal 7? And obviously it's easier to ditch 1. Yes, you guys, there are free electrons shooting around. And in fact, they discovered electrons because they were messing with those old photographic plates. And you keep those, from being exposed to light, and then you'd use them and there'd still be this like zingy line through it. And so that's actually what led them to the trail to discovering these electrons. So there's electrons out there too that have been ditched or to pick up and steal. So if you lose an electron, you will become positively charged. Well, let's look at element number 9, or fluorine. Fluorine has 7 in its outermost shell. It's got 2 in the first shell and then 7 in the second shell. Remember, the second shell is full with 8. And so fluorine, it's going to grab 1 and fill it in. So it's still fluorine inside. It still has 9 protons. But now it has 10 electrons. It's cross-dressing like neon. Okay, and so it's wearing the noble gown of neon, but it's still fluorine inside. So it will actually end up with a -1 charge. Now, when we talk about bonding, obviously positives and negatives, they're not happy by themselves. And opposites attract in chemistry, and they're going to come together to balance that. All right, we sort of gave you a little hint earlier about isotopes. Remember I was saying about carbon-14, and then I told you that you and I have carbon-12 in us. There's also another isotope of carbon that's called carbon-13. Now, an isotope is just an element with varying number of neutrons. So carbon-12 is the most common type, then less common is carbon-13, and even less common is carbon-14. They're all carbon. They all have 6 protons in their nucleus. Okay, but what differs is carbon-12 has 6 neutrons. Carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. And this happens naturally, okay? We're not messing with it. So that's why that atomic mass is kind of important. Now, we're not going to really concentrate on isotopes at this point. It'll be next exam when we talk about radioisotopes, because remember, that's how we date rocks and we date things. So that's pretty darn important, also as a power source. So we're going to come back to it at a later time. But right now, all you need to know is that isotopes are elements with varying number of neutrons. Now, you guys, quick heads up. Most elements have isotopes, okay? It's more than norm. It's actually not very normal to not have some variation in your element. Remember, the number of protons doesn't change. You just vary the number of neutrons, and that does change the mass. All right, well, here's just an example, you guys. Carbon-12, carbon-13, carbon-14. You know, check it out. They are the same in that they all have 6 protons, but you and I have the carbon-12 again, 6 neutrons, carbon-13 has 7 neutrons, carbon-14 has 8. All right, bonding. So we're going to come up with bonding. Bonding is pretty important. Think about it. You like to drink H2O. Okay, now when elements come together, and remember, the only elements that are not going to like hook up or bond with somebody are the noble gases, that far right-hand column. Every other element cannot exist on its own happily. It's got to hook up. Okay, there's O2, O3, H2O, CO2. O never lives by itself. Oxygen. That's why, you know, oxygen is very reactive. You don't smoke around an oxygen tank. It will blow up, just like you don't smoke around a helium tank or a Zeppelin full of helium. Okay, what you do is, you know, you got to come together to try to be more stable. All right, there's 2 different types of bonding, and this is kind of important. Ionic bonding. Remember, ions are positive or negatively charged elements. And then there's a second type called covalent that I haven't talked about yet, and we will. All right, ionic bonding. First thing to say, though, about bonding is that when 2 elements come together, first of all, if you have, you know, let's say sodium and chloride. We've got pictures of sodium and chlorine right here. When it comes together, it's going to be table salt, and most of us have no problem with table salt. Okay, but if you think about it, sodium is a metal if it was all by itself, and it is really reactive. It will blow sky high. Do not put a piece of sodium metal in your pocket. Okay, chlorine gas. Let's go back to World War I and II in the trenches. Mustard gas, yeah, it's bad. So how can 2 deadly things come together to form something like table salt or halite? And in fact, we probably wouldn't have civilization if it wasn't for salt, because how did you preserve meat for, you know, larger populations of people if you didn't have a preserving agent like salt? So it's pretty darn important. Now, the sodium, remember, look at it. It's got 1 extra electron in its outermost shell. It's going to ditch it. Okay, and it doesn't have to go to chlorine. It can be ditching it, and now it's got a positive 1 charge. Okay, the chlorine, it's got 7 out of 8 in its outermost shell. It's going to steal 1, stick it in there. And so now it's going to have a negative charge. Positive 1, negative 1, they come together, and they come together beautifully. Okay, now these are ionic bonds. You guys, if I have a big halite crystal, I don't know if you've seen like rock salt, if you throw it in water, water breaks it apart. Ionic bonds are really weak. And water, we're going to find out, water does nothing but tear these things apart. Water is the universal solvent. It breaks ionic bonds. All right, there is a second type. Check this out. This is water, you guys. H2O. 2 hydrogens, 1 oxygen. Now, this is not stealing and ditching. This is sharing. Okay, and these bonds are much stronger. Hydrogen, each of those hydrogens has 1 electron in its outermost shell. The oxygen has 6 electrons in its outermost shell. Now, if you remember when I said that those electrons are everywhere at once, that was kind of important. Because of that, the outermost shell of each of these elements overlaps with each other and shares 1 electron. And because they're everywhere at once, they both think they have it. So if you count in the hula hoop for hydrogens, they have 2. That's cross-dressing like helium. And if you look for the oxygen, it has 8. So it's cross-dressing like neon. So they have obtained electron stability, okay? And also a really, really strong bond. Okay, quartz is completely covalently bonded. If you pick up a big quartz crystal, it will scratch glass. Diamond is completely covalently bonded. These are strong, strong bonds. Okay, if I toss a diamond or a quartz crystal in a bucket of water overnight, all I'll end up with is a clean mineral. They're not going to dissolve away. All right. If you are in lab, you will spend time looking at things like, is it metallic or non-metallic? Does it scratch glass? Does it leave behind a colored streak? And all of these are really, really important. And if you remember, it's this regular repeating internal structure that dictates all of the properties that these mineral hand samples have. But we will go over a few of these. All right, so here's a list, and you guys, I have slides for each and every one of these. And if you are in lab, which hopefully you are, you will get a chance to make sure that you really understand each of these properties. Now, the first one, crystal form, it's not that bad. You guys, if I held up a quartz crystal, and I do this in class, I hold up a quartz crystal and say, hey, you guys, what's this? And everybody says, quartz. Okay, you recognize it by its ideal crystal form. Okay, color. Now, I'm going to warn you about color. I can give you the same mineral in 10 colors. So color's not great, but we always note color. Now, streak. Streak is kind of cool. Streak, we don't use color. Like if you just look, I can show you quartz in clear, white, purple, yellow, pink. But if you streak a mineral, and a streak is the color of a powdered mineral. If you're in lab, we have these little shower tiles that are non-glazed, and the softer minerals, you run them across the porcelain plate, and it'll powder the mineral. And you look at the color, and sometimes a black mineral will leave a clear streak or a green streak, and sometimes a silver mineral will leave a red-brown streak. It's the streak, or the color of the powdered mineral, is way more indicative of what mineral you have than just the color of the hand sample. All right, luster. Luster is the way light is reflected off the surface. It's just, is it metallic or non-metallic? Don't write down all the names that I put down because, metallic and non-metallic, that's kind of important. Now, some metallic things are shiny, some are not. And then after that, it's just names that you kind of come up with, okay? And I'll explain a little more. Now, probably the single most important characteristic of a mineral is its cleavage. And this is like if you told me I could only use one property to identify minerals, and I had to bet all my money, okay, I would use cleavage. And cleavage is a way a mineral breaks. I'll explain more about it. I call it the sledgehammer test, and we're going to talk about this. All right, density. You could actually probably identify every single mineral by doing a density test. You would weigh your hand sample, okay, figure out its mass, and then you would put it in water and see how much volume is displaced, and then divide that volume by the mass by the volume and figure out its density. The density of quartz is something like 2.7 grams per cubic centimeter. So all of the minerals have their own kind of specific density. So density is important. I only use it for what I call the heft test. A lot of times if you have a metallic mineral in your hand, you're like, wow, that's really, really heavy. So that's kind of what I call the heft test. All right, hardness is important. One of the very first things we do in lab is we see, does my mineral scratch glass? If it scratches glass, that tells us something. It tells us it's got a lot of strong bonds. So we'll talk a little bit about Dr. Moe, okay, and his hardness scale. All right, crystal form. Crystal form is ideal crystal form. Quartz crystals, you guys, you know what a big quartz crystal looks like. You've walked by a mineral store or you've seen one of those people that worship minerals. There's a ton of quartz right outside all over the ground in Rockland. Okay, but most of it is absolutely not ideal because in order to have those big fingers of quartz, you got to have space to grow into. So if there is no time constriction, if you got all the time in the world and you have all the space in the world, your minerals will grow absolutely perfectly ideal. Think about, where do you find, big quartz fingers? You usually find them in geodes or open spaces, okay? But granite, I think all of you guys know what granite looks like. There's usually, in most granite, there's a lot of quartz, okay? But it doesn't look like those fingers of quartz. So you gotta have space, you gotta have enough time. And if you don't, you still have the exact same regular repeating internal structure, the same chemical formula, it's just not in its ideal form. All right, here are those fingers of quartz. Now look at the bottom of this picture. That's not ideal, that's not pretty because it's growing up against a surface. But the fingers themselves that point upwards, they grew into an open space. So that's kind of ideal crystal form. Okay, I'm going to give you a little warning about not to confuse this with cleavage here in a minute. All right, here's a piece of granite, and in that granite you can see there's some smoky quartz. We'll talk about those other two minerals. Now, that poor quartz has neighbors, and those neighbors grow too, and it grew, and it has the same exact